At the start of the last Jason Bourne movie, the journalist Simon Ross goes to his source and shows him a set of pages from newspaper and police bulletins and asks the question, what connects the dots? Well, that's the question I'm asking here when I show you a picture of a bird, a pied cormorant, some 5-cent pieces, a few eggs, and this equation. What connects the dots? The answer to that question is the binomial distribution. Coins, when they're tossed, can come down heads or tails. That's a binomial situation because there are only two possible outcomes, a head or a tail. Eggs might not seem to be a binomial situation, but in fact they are, because they can hatch out to be either a male or female chick. So each of those 3 eggs is a binomial trial, as is each of those 3 coins, and they are very similar. Given no further information, the best guess we can make is that an egg has an equal chance of coming out male or female, just as a coin has an equal chance of coming down heads or tails. A third piece of relevant information here is that the pied cormorant lays clutches that usually have just 3 eggs. So it's a useful situation to think about how we can use the binomial formula and the binomial distribution. So that formula, you can see there is the binomial formula, and we'll look a moment at how it's used. Yesterday in class, I got the students to pretend that they were pied cormorants and that they were going to lay a clutch of eggs. The way I did that was to give each of them 3 5-cent pieces and ask them to toss those coins, and then to record the outcome. And we'd call a head a female chick and a tail a male chick. So in the set of outcomes you can see on screen here, we've got 2 heads, so that's 2 female chicks, and 1 tail, so we've got 1 male chick. So that would go as a tick in this column over here. Now I got each student to toss the coin several times and to record the outcome each time they tossed their 3 coins. And what you can see in the table here in the counted row is what we found. On 10 occasions, the coins came down with 3 tails, or the clutch had 3 male chicks and no females. On 8 occasions, we saw the reverse outcome. 3 heads, meaning 3 females, and no male chicks. And the other outcomes were a mixture of male and female chicks, either 1 male and 2 females or the reverse. And you can see that those outcomes happened 25 times and 17 times. So approximately 2 to 3 times as common as clutches that had only female chicks or only male chicks. Now, running a little simulation like this is a good way and a perfectly acceptable way of working out what we might expect to see. But it is a little time consuming, and if we increase the number of clutches or we want to get more reliable results, it's going to be more complicated and take us more time to do. So that's where we can use the binomial formula. And the binomial formula allows us to work out the probability of getting a particular set of outcomes. And if we work out each of the possible outcomes, we've worked out the binomial distribution for that situation. And I'm using the term distribution here because we're talking about a set of outcomes. So with 3 chicks, we have 4 possible outcomes. We have no females, 1 female, 2 females, and 3 females. Those outcomes form a distribution, and we can easily plot a little graph that shows us that we have a count of 10, or a frequency of 10 cases where there were no females, 25 with 1, 17 with 2, and 8 cases where all the eggs hatch out to be females. That's a distribution. That's an observed frequency distribution. Getting back to the binomial formulator and calculating out what we expect to see, this is the formula we need to use. Now, it's a little complicated, but it breaks down quite simply. N factorial, the exclamation mark there, means factorial, divided by r factorial times n minus r factorial. Well, hang on, what's n here? What's r? And then if I go a bit further on, I've got times p to the power of r times 1 minus p to the power of n minus r. So what's p? Right, before we start using the formula, we need to establish the situation we're working with. We need to specify the key criteria. So we look at this situation, n is 3 because we are tossing 3 coins, or we're looking at the outcome for 3 chicks, 3 eggs. So n is the number of trials, it's 3 in this case. P is the probability of success. Now success is used because a lot of early probability was involved with gaming and chance outcomes. So if we call a female a success, then the chance of getting a female we can assume to be 0.5 or 0.5. We assume it's 50-50 because we assume there's nothing causing males to be more or less likely to hatch than females. That might be wrong, but it's a good starting assumption. Then finally, R refers to the number of successes we're considering at that particular time. So to start with, we'll look at R equals 0. We'll look at the first case where there are no female chicks. Then we'll look at R equal to 1 for 1 female chick, and so on until we've worked out the probabilities for the entire distribution. So substituting values in here, I get the probability of 0 females is equal to 3 factorial divided by 0 factorial times 3 minus 0 factorial, so that's 3 factorial, times 0.5 to the power of 0 times 1 minus 0.5 to the power of 3 minus 0. Okay, factorial. What is factorial? Factorial is easier to illustrate than to explain. So 3 factorial is just 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 0 factorial is defined to be 1. So simplifying this equation, we've got 3 factorial divided by 3 factorial gives us 1. 0.5 to the power of 0 is 1, because any number to the power of 0 is 1. And then we've got 0.5 to the power of 3. And 0.5 to the power of 3 is 0.125. So the probability of getting no females in a clutch of 3 eggs, if the chance of males and females is equal at 50%, is 0.125, or 1 chance in 8. Now, we can continue to work out the probabilities of the other sets of outcomes. So for the situation where we get 1 female, we simply change the value of R to be 1. So we've got 3 factorial over 1 factorial times 2 factorial, 0.5 to the power of 1 and 0.5 to the power of 2. So that's 3 times 0.5 times 0.25, 0.375, or 3/8. We can do the same for the next outcome. Chance of getting 2 females and 1 male. And now we've got 3 factorial over 2 factorial times 1 factorial, 0.5 to the power of 2, 0.5 to the power of 1, which is 3 times 0.25 times 0.5, or 0.375 again. Now at this point, you can see there's a bit of symmetry going on here, and the outcome here is very similar to the outcome there, with just the 0.5 and the 0.25 switched around. And that is the case whenever the probability of success and failure is equal at 0.5 or 50%. So once I've worked out the probabilities for 0 females and 1 female, I can actually just write in the other two, because the chance of 1 male and 2 females will be 0.375, as I've just shown you, and the chance of no males and 3 females will be the same as the chance of no females and 3 males, or 0.125. So what we've worked out now is the chance of each of the different outcomes. We worked out the probability distribution. It might then be useful to ask, well, how well does what we see match up with what we would expect to see if the chance of males and females is 0.5, if this really is just a simple binomial situation with a probability of 0.5? Well, we can work out the number of clutches we would expect to see with 0 females just by multiplying the probability of that outcome by the total number of clutches we're looking at. And in this case, if we add up 10, 25, 17 and 8, there's 60 clutches in our sample there. So 0.125 times 60 is 7.5. 0.375 by 60 is 22.5. And the same is the expected number for 2 females and 1 male. And 7.5 again is the expected number for 3 girls, no boys. So I can write in the expected numbers there, and you can see that the expected numbers are very similar to what we've actually observed. There's some slight differences, but they're not huge. So we've got a little bit more, or slightly more, clutches with all boys than we would expect, and slightly more clutches with 2 males than we would expect to see, and slightly fewer of the other outcomes. But there's not a huge difference between what we observed in a little simulated trial for pied cormorants and what we would expect to see if the chance of males and females is 0.5.